All right, so in this problem, we're going to combine rotational dynamics and kinematics, and we're going to see how those work together. So a disco ball, which is basically a solid sphere, is being set up in a dance hall at the center of the room. It has a mass of 6.5 kilograms and a radius of 27 centimeters. It's going to be set into rotation about its center of mass from a rest position using a mirror ball motor. And we're looking for a final desired rotation speed of 5.6 RPMs, or rotations per minute, after a time of 10.4 seconds. Okay. The first part of this question is asking us to calculate the moment of inertia of the disco ball. So in order to calculate the moment of inertia of the disco ball, if I assume that it is a solid sphere, I can pull my equation for the moment of inertia of a solid sphere. That is, I equals, the moment of inertia equals 2/5 times the mass of the sphere times the radius of the sphere squared. I got that from my moment of inertia chart. So this constant here was 2/5. That would be equal to 2/5 multiplied by 6.5 kilograms. And then in this case, I'm going to use meters. So 0.27, move that decimal place over 2 to the left, meters squared. That would give me a moment of inertia of 0.190 kilogram times meter squared. All right, so that's it for the moment of inertia. So if we're asked then in part B to solve for the magnitude of the angular acceleration required, so remember we were told that we want this final rotation speed, that's our design criteria, after this amount of time. What does my angular acceleration need to be in order to get to that speed in this time from rest? Now, I know that I can get alpha, my angular acceleration, from net torque, but I don't know anything about the net torque right now. So instead, I think I have enough information to use rotational kinematics, and that's what I'll do. So in previous problems, we used net torque to get angular acceleration, but this time we're going to use kinematics first to get our angular acceleration, and then we'll use that after to look at our torque. So I'm going to write out my given information for rotational kinematics then. That would be the time was 10.4 seconds. I know that my initial angular velocity is 0. This is not rolling motion, right? The disco ball is spinning in the air. So I'm not going to consider any of my linear variables at the moment in time. But I know my initial angular velocity was 0 because it was at rest. And my final angular velocity is 5.6 rotations per minute. Okay, so I already know here I'm going to have to convert this. I don't want rotations and I don't want minutes. I want radians per second. So I'm going to convert that just right now, right away, before I do anything else. If I have 5.6 rotations per 1 minute, I'll do them both at the same time using dimensional analysis. I know that one rotation is 2 pi radians, right? So I know my rotations go away. That would give me radians per minute now if I just stopped, but I want to keep going. I know that 1 minute has 60 seconds. And so my minutes go away now, and now I'll have radians per second like I wanted. That means that the final angular velocity, if you were to calculate this, is going to be equal to 0.59 radians per second. And again, I'm storing all of these values in my calculator as intermediates so I don't introduce rounding error. Or if you're not doing that, then at least write out 3 or 4 decimal places for intermediate values like what I've just done here. Also, please make sure when you're putting pi into your calculator that you use parentheses. So I would do 5.6 multiplied by, in parentheses, 2 pi, and then you can divide that by 60 if you want to. I've noticed that when you don't put parentheses with pi, calculators often use the wrong order of operations. So just be very careful whenever you're using pi that you're also using parentheses. All right, so now that I've defined all my given information for rotational kinematics, I see here that I can very easily use this first equation to solve for alpha. Alpha is the only thing I don't know. I know my time and my initial and final angular velocities. So if this is my equation, I'm going to rearrange this equation for alpha. I'm going to move the omega initial to the other side and divide by time. And that gives me omega final minus omega initial over time is equal to alpha. And I know that that's actually just the definition of alpha, right? This whole thing, if I look at this, this is just the same thing as delta omega, which I knew was the definition for acceleration, okay? So this is just equal to, right, that 0.59 radians per second, again, minus 0, over my time, 10.4 seconds. So my angular acceleration is equal to 0.0564 radians per second squared. I know it seems very small, but disco balls don't spin very fast, so this isn't outrageous for what we're dealing with here. Okay, let's take a look at part C on the next slide. So now we're asked to solve for the torque that the motor needs to provide on the disco ball. So we can assume that the disco ball is probably attached to some shaft through its center and the motor is spinning that shaft. We don't really need to worry about the geometry here because we're not solving for the torque using lever arm. We don't have enough information to do that. Instead, we can solve for the torque using our Newton's second law rotational form, right? We know that the net torque is equal to the moment of inertia times the angular acceleration. I only have one torque in this case. I'm ignoring like any torque produced by air resistance or friction. I just have the motor. So I only have to worry about that single torque. I already know I, my moment of inertia, and I just solved for alpha. So I'm just going to go ahead and plug those in here to solve for my net torque. My net torque then would be equal to 0.0107 Newton times a meter. And so once again, I used the exact values here in my calculator. I'm using them as rounded values for example purposes, but I've stored these values in my calculator when solving for my torque. And I know, again, this is a very small torque, I understand, but it's not unreasonable for what we're dealing with here. 5.6 rotations per minute is not a very fast rotational speed. And so in this case, the net torque needed to provide that rotation isn't very significant. I also want to point out that I am using the units of Newton times a meter. I know it's getting less intuitive how the units work out here, but just as a refresher, right? Kilogram times meter squared times radians over second squared. The radians just kind of go away. This is, right, if I think about it like this is actually, this whole thing is a Newton times, this is meters squared, so times another meter, I get my Newton times a meter. So my units work out just okay. All right, and this has been an example of solving a problem by first solving for the acceleration using kinematics, and then using that acceleration in dynamics to solve for my torque. So a useful way to solve problems. Again, it doesn't always begin with kinematics or with torque. You kind of have to gauge the information you're given and where you're trying to go to plan your problem-solving process. Okay, this concludes our series of videos on rotational inertia and rotational dynamics. Please take a look at Canvas for some practice problems to continue to develop your skills.